Kafka powers some of the world's largest data pipelines and real-time streaming applications. But for many, getting started feels overwhelming. In the next few minutes, we'll break down the essentials into straightforward, bite-sized concepts. Let's start at the top. What exactly is Kafka? Think of Kafka as a distributed event store and real-time streaming platform. It was initially developed at LinkedIn and has become the foundation for data-heavy applications. Here's how it works. Producers, essentially the sources of our data, send data to Kafka brokers. These brokers store and manage everything. Then consumer groups come in to process this data based on their unique needs. Now onto messages, the heart of Kafka. Every piece of data Kafka handles is a message. A Kafka message has three parts: headers, which carry metadata, the key, which helps your organization, and the value, which is the actual deployed payload. This structured approach is what makes Kafka so efficient at handling large volumes of data. Now that we understand what a message is, let's look at how Kafka organizes these messages using topics and partitions. Messages aren't just tossed into Kafka. They are organized into topics, categories that help structure the data streams. Within each topic, Kafka goes a step further by dividing it into partitions. These partitions are key to Kafka's scalability because they allow messages to be processed in parallel across multiple consumers to achieve high throughput. So why do many companies choose Kafka? Let's talk about what makes it so powerful. First, Kafka is great at handling multiple producers sending data simultaneously without performance degradation. It also handles multiple consumers efficiently by allowing different consumer groups to read from the same topic independently. Kafka tracks what's been consumed using consumer offsets stored within Kafka itself. This ensures that consumers can resume processing from where they left off in case of failure. On top of that, Kafka provides disk-based retention policies that allow us to store messages even after they've been consumed, based on time or size limits we define. Nothing is lost unless we decide it's time to clear it. Finally, Kafka's scalability means we can start small and grow as the needs expand. Now let's look at producers, the applications that create and send messages to Kafka. Producers batch messages together to cut down on network traffic. They use partitioners to determine which partition a message should go to. If no key is provided, messages are distributed randomly across partitions. If a key is present, messages with the same key are sent to the same partition for better distribution. On the receiving end, we have consumers and consumer groups. Consumers within a group share responsibility for processing messages from different partitions in parallel. Each partition is assigned to only one consumer within a group at any given time. If one consumer fails, another automatically takes over its workload to ensure uninterrupted processing. Consumers in a group divide up partitions among themselves through coordination by Kafka's group coordinator. When a consumer joins or leaves the group, Kafka triggers a rebalance to redistribute partitions among the remaining consumers. The Kafka cluster itself is made up of multiple brokers. These are servers that store and manage our data. To keep our data safe, each partition is replicated across several brokers using a leader-follower model. If one broker fails, another one steps in as new leader without losing any data. In earlier versions, Kafka relies on Zookeeper to manage broker metadata and leader election. However, newer versions are transitioning to Craft, a built-in consensus mechanism that simplifies operations by eliminating Zookeeper as an external dependency while improving scalability. Lastly, let's quickly touch on where Kafka excels in the real world. It's widely used for log aggregation from thousands of servers. It's often chosen for real-time event streaming from various sources. For change data capture, it keeps database synchronized across systems. And is invaluable for system monitoring by collecting metrics for dashboards and alerts across industries like finance, healthcare, retail, and IoT. If you like our videos, you might like our system design newsletter as well. It covers topics and trends in large-scale system design, trusted by 1 million readers. Subscribe at blog.bytebytego.com.